Alright, so now let's put everything together from start to finish to be able to use the normal distribution to approximate binomial probabilities. So the first thing we want to do is just make sure that we can use the binomial distribution first off. So make sure you have a binomial probability in the first place. So make sure that you know what your N, P, and Q are. The second step is you want to make sure that you can use the normal distribution to actually approximate the binomial variable R. So remember, to do this, you need to ask yourself the two questions. Is NP greater than or equal to 5? And is NQ greater than or equal to 5? Remember, if either one of those questions you answer no to it, then you cannot use the normal approximation. The third step, so once you know you can do this, find the mean and standard deviation for the normal distribution, which is going to be the same as your mean and standard deviation of your binomial distribution. So mu is going to equal to n times p, and sigma is going to equal to the square root of n times p times q. Next, you want to get equality and then apply continuity correction. And then get from there. So to do that, you want to add or subtract 0.5 depending on if you have left hand, right hand, or both endpoints. And from here, shade your normal area. And then from there, it's the exact same stuff we did back in sections 6.2 and 6.3. So from there, you find your z-score, find the probability using your z-score table. And that's it. So let's look at one of these all the way through. So 62% of adults in the U.S. have an HDTV in their home. You randomly select 45 adults in the U.S., ask them if they have an HDTV in their home. What's the probability that fewer than 20 of them respond yes? So this is the one we already looked at earlier. And so remember, we found out that yes, you can use the normal approximation in this case. So we had specified N was 45, P was 0.62, or sorry, 0.45, no, 0.62. So P is 0.62, and Q is 0.38. And so we had already found, remember, NP and NQ, we had already found these. We found NP was 27.9, NQ was 17.1, both were larger than or equal to 5. And so that told us we could do it. So then we know mean, in this case, mu is our n times p, which was 27.9. We've already calculated that. And standard deviation sigma is going to be about 3.26. So we already calculated that earlier. Alright, so we know that we're trying to find the probability that fewer than 20 of them respond. So this is R is less than 20. So this is the probability R is less than 20. So the first thing we need to do is get our equality. So this is going to be, remember, since it's less than, we're going down. So this is going to be R less than or equal to 19. And now let's figure out, okay, left hand or right hand. So sketch out a number line. There's 19. And it's less than or equal to that. So this is our right hand endpoint. So we have to add 0.5 to convert to x. So this is the probability that x now is less than or equal to 19.5. And it's perfectly okay if after you convert to x, if you omit the equality. So you might see it written as just x is less than 19.5. That's okay. Because remember, once you've converted to a continuous random variable, the equality itself has no meaning because we know the probability that it's equal to some value is just equal to 0 at that point. So we can omit the equality without changing anything at that point. I'm typically going to write it with the equality just so that we remember the original probability was with equality since it was binomial. Alright, so we've got probability x is less than or equal to 19.5. So now let's go ahead and convert to z. So we're doing another calculation. So z now less than or equal to, so our z-score formula, 19.5, our data value, minus our mean of 27.9, divided by our standard deviation of 3.26. So this becomes probability that z is less than or equal to negative 2.58. So now let's sketch our normal distribution, see what we're looking at. So here's our z distribution. Negative 2.58 is about here. and we want less than or equal to. So we're looking for area to the left. So we just go to our table. And on our table, we're going to look for negative 2.58. So remember, you go down to negative 2.50 here on your left-hand column, and then go to 0.08, so our hundredths digit. Find where that row and that column intersect, in this case 0.0049. And because we're looking for less than or equal to, which is what our table gives us, that is our probability. So approximately 0.0049. Alright, so let's look at one more example. So a survey reports that 62% of internet users use Internet Explorer as their browser. You randomly select 150 internet users and ask each whether they use Internet Explorer as their browser. And we want to know what's the probability that exactly 96 will say yes. So, same idea. First thing we need to do is check, is this binomial? So, do we have a fixed number of trials in? So, in this case, we know that we're selecting 150 people, so that's our N. P, probability of success. In this case, it's going to be, we want to know not exactly 96 will say yes. So, success is going to be that they say yes, they use Internet Explorer as their browser. In this case, P is 0.62. And then Q is always going to be 1 minus 0.62. So Q in this case is going to be 0.38. So now we do our check to make sure that we can use the normal approximation. So N times P is 150 times 0.62. And so we get 93, which is greater than or equal to 5, so we're good. N times Q, 150 times 0.38, which is 57, which is greater than or equal to 5, so we're good. So we can do our normal approximation, so it does apply in this case. And so then we need to find the mean and standard deviation of the binomial. So mu in this case we've already calculated is N times P, so we know our mean is 93, and our standard deviation then is square root of 93, so N times P times Q, so times 0.38. And so we do that and we get about 5.94 rounding to 2 decimals. So then, continuing on, so figuring out the probability. So we want probability that R is equal to 96. Now, we know for this to be equal to a value, then from continuous can't be equal. So we need to find a way to rewrite R equal to 96 as R is between two values. So that then we can do our continuity correction to convert it to X is in between two values so that we can actually find this. So knowing that R is equal to 96, that's going to be the same thing as saying R is less than or equal to 96 and greater than or equal to 96. So R is only between 96 and 96. So if it's equal to it, then it's going to be between the same value. There is no difference of values. So both our left and our right endpoint are 96. Which then means now we can do our continuity correction. So we have in between two values, 96 and 96. So that means we subtract from the left hand, add to the right hand to do our continuity correction. So this becomes the probability that X now, doing our continuity correction, 95 is between 95.5 and 96.5. You should also recognize these again as your class boundaries from like we did back in chapter 2. Alright. And so then from here, we know this is the probability that X is between 95.5 and 96.5. So we can convert to Z. So doing our Z-score calculation, in this case twice, we have 95.5, our data value, minus our mean of 93, divided by standard deviation of 5.94 is less than or equal to X, which is less than or equal to Z, because we're doing our calculation to convert to Z now, less than or equal to 96.5 minus 95.5 divided by 5.94. And so this gives us the probability that Z is in between 0.42 and 0.59. And so now sketching out what this looks like. So there's our z distribution. So here is 0.42. There is 0.59. And so there's the region we're trying to find. And so we look up 0.59 on our table, and we should get 0.8212. Minus looking up 0.42 on the table and getting 0.7611. And so when we do the subtraction, we should end up getting the probability that z is between those two values, which is the same thing as the probability that r is equal to 96, approximately, should be 0.0596. And so now you should go back and use the binomial formula to check this probability and see how close it actually is.